להראות את החץ. All right, good morning. For me, it's a special pleasure to be here. It's also 50 years since I personally first heard about the Aharonov-Bohm effect in a lecture by David Bohm at the Hebrew University, which was very impressive. The most impressive part was that Rakach was sitting there. In the beginning, it was going like that. In the end, it was going like that. So it was so simple that anyone, even me, could follow it. So 10 years later, I started with this obsession, which is, I think, the first application of the Aharonov-Bohm effect to mesoscopic physics. And I decided to talk just about that, because that, I think, has everything. And this is called the equilibrium persistent current in a mesoscopic ring. So as you see, there is a span of about 40 years' work on this problem. And there was a puzzle that existed until, say, 2 years ago. We think we've solved it. We're not sure that this is the solution, but it's a possible solution. Now, I don't have to repeat here that Aharonov-Bohm flux in a closed ring is equivalent to a boundary condition. And then there is the very celebrated Byers-Young theorem, which is a real theorem, which is rigorous mathematically and, unlike many other theorems, also very relevant physically, saying that all the physics of this ring with great generality is periodic in the flux with a period h over e. And that's simply because we know that a flux is equivalent to a phase change, and that's only relevant modulo 2 pi. So that's something to keep in mind. Now, if the free energy, now I'm talking about equilibrium physics, if the free energy of this system depends on the flux, non-trivially, if it's a constant, then nothing happens. But if it changes with the flux, then there will be a current flowing in this ring in equilibrium. And that's quite interesting because usually in normal conductors that doesn't happen. In fact, Byers and Young emphasized why superconducting long-range order is necessary in order to have persistent currents. What they didn't do, and I was dying to talk to Professor Young about it here, they didn't care to consider the case of a finite system, which is really how mesoscopic physics is starting. If you go to a finite system, you can have a current flowing in a normal conductor in the presence of flux, which will never decay. And this is really what I'm talking about, and I'll talk a little more about the details of this. And the real interesting issue is that impurity scattering or defect scattering, which generally in condensed matter physics we know that it will scatter electrons all around the place and kill any transport current, does not kill this equilibrium current. So if you make this current flow by a voltage, there will be dissipation, the current will dissipate. If you make it flow with a flux, it can go forever and will not decay in spite of impurities. I'll come back to that, but it's actually almost trivial once you understand it, of course. I'd like also to say that there is a prehistory to this problem. There are old papers by Hund, London, Pauling, quite not weightless scientists who looked at the magnetic response of what is called aromatic molecules, such as benzene, naphthalene, anthracene. And those are known to have this is anthracene, okay. Those are known to have a very large diamagnetic response, and actually explain this magnetic response as currents that flow around the molecule in the presence of a magnetic field. Their calculation actually invoked the AB effect, but they didn't understand that. They thought it was due to the magnetic field. They didn't really say anything about that. So actually, London, for example, has done a calculation very similar to what we call now the tight binding approximation, demonstrating that in this system there are such currents. Now, the problem is that it's only atomic scale, molecular scale, and people say, okay, it's valid on the molecular scale. It's certainly not valid in the macroscopic limit. No currents flow. So, okay. But then the question is, what happens if you go to intermediate scales? to scales in between macroscopic and microscopic. And it's there where new things start to happen. Also, they did not have the impurity scattering to worry about. And that's really a very important part of the problem. So I've here summarized the questions. And the interesting issue now is to try to go in between the microscopic and macroscopic regime and see if you can somehow benefit from both worlds. So again, if you forgot, here is the gauge transformation. I'm sorry, that makes, okay, I don't know how to go, how do I go back? This is the gauge transformation that makes you be able to trade flux for phase. And this is again reference to the very basic paper by Byers and Young, which I recommend for those who don't know very, very much to read carefully, including the explanation of off-diagonal long-range order, which actually is not applicable to finite systems. Now, the issue is then what happens when you have a real system, a system that is not perfect, and whether those imperfections can scatter the current. And actually, when I was talking about these issues, even up to about 10 years ago, people immediately said, we know that if electrons flow, they hit impurities, they scatter in other directions, so an ordered flow becomes a disordered thing. The entropy increases, and therefore this should dissipate and disappear. Now this is correct only in classical physics. Classical physics, you have this picture. In quantum mechanics, you just don't have this picture. You have a quantum state. Quantum state has a wave function. If in that wave function the current operator has a non-zero average, then current will flow. So this classical picture is simply very misleading, and this was demonstrated by Buttiker, who is, I guess, not here, but was supposed to be, Landauer and myself some years ago, by making an analogy to another tight binding model, but I won't go into this. I just take 1 minute to really flash, just show you that there are quite many experiments on this. This is the first experiment, I'll come back to it, which demonstrated very clearly currents that flow, which are periodic in the flux. Then more experiments came, very ingenious one. It's a very difficult thing to measure because the currents are small. In the beginning, they were just measured by looking at the magnetic moment that they produce with a squid. There were quite a number of very ingenious, beautiful experiments on this. This peak is the manifestation of the periodicity with period h over E. The most recent experiment, actually whose physical results were published in Science last Thursday, is by the Yale group. The student is Anya Bleshinsky, and the advisor is Jack Harris, who invented this experiment. This concept is this is the ring. The ring is a magnetic moment as a result of the current. You put a magnetic field perpendicular to the magnetic moment. There is a torque. The torque bends this cantilever and changes the vibration frequency of the cantilever. By measuring that, they can measure the flowing current. Turns out it's very sensitive, and it has a lot of other good things. Another very recent experiment is using this scanning squid technique, which was mentioned in Chang Tsui's talk a few minutes ago, to hover around above a system of many, many rings and measure their magnetic response. So even in the last years, there is a kind of awakening of the interest in doing these very, very difficult experiments, and we are very hopeful that things will become even more interesting in the next few years. The first theoretical attempts to calculate the magnitude, now we understood why there can be a current, but what's the magnitude of this current? So you do it for non-interacting electrons, and you find that for any single ring, the magnitude of the current is related to what is called the Thouless energy of the system. And I just want to flash it here. L is the circumference of this ring, and this is the energy associated with the diffusion constant, with the diffusive motion due to impurities of an electron around the ring. And this energy is the energy that governs most mesoscopic phenomena, because it's really the energy which has to do with the finite size of the ring. And I'll get into this energy scale more and more as a function of time. Be it as it may, the current in a single ring is on the order of this energy. You divide by the flux quantum, you get a current. So energy and current are just related by a universal constant. In this slide, delta is the level spacing, which is not so relevant. And this is for one ring. Now, the problem is that for non-interacting electrons, the sign of the current or the phase of the oscillations as function of flux varies from sample to sample. And if you average it over many, many samples, you get almost zero. You get a very minute result, and the details are not so important. But the first experiment which I showed, you remember, had many rings, actually had 10 million copper rings, and it produces a the result on the order of the Thouless energy divided by the flux quantum. That's very strange because we said that their sign is random, so it should have been much, much less, divided by 1 over square root of the number of samples in the system, and it was not. So that was the puzzle. That started the attempts to understand more seriously what is the magnitude of this current. And it's clear that if it's much larger than what you get from non-interacting electrons, then you must be a grown-up and start to deal with the interaction. And what does a theoretician do? He uses perturbation theory in the interaction. And the first attempt is to use perturbation theory in the dimensionless interaction. The interaction is V. I'm sorry, again. I cannot use this. Okay. There is here something that looks very benign, and that would be perhaps the main subject of my talk. You notice this denominator here. So lambda is a dimensional interaction. The current is proportional to first order to the Thouless energy times lambda. Lambda is the dimensionless coupling constant. It's about 0.6 in copper. So in the beginning they were very happy. They said, look, we just have EC over phi naught times lambda. And that's almost the order of magnitude of the experiment. But that's not the end of the story, because of this thing here. This denominator is called the renormalization of the interaction when you go from high energies to low energies. It's not a new thing in physics, but in this, actually, it appeared a lot in other branches of physics with other names. Here it was discovered by Tolmachev immediately after BCS, and Anderson and Morel explained it clearly. This is what happens when you renormalize the interaction from the energy scale of the Fermi energy, of Coulomb energy, to the temperature at which you live. And that reduces the effective interaction by almost an order of magnitude and kills the agreement with the experiment. So this is where things are. The theory gives you a result smaller by a factor between 5 and 10 than the experiment, and that was done in 1990. And for about 18 years, nobody could really understand why the experiment is giving almost an order of magnitude more than the theory. So that was the puzzle. So, okay, we summarize it here. We don't have to talk about it. About 2 years ago, there is a piece of work by Hamutal Bari-Soroker, my student, and Ora Entin-Wallman and myself. And we try to understand this renormalization a little bit more, and we propose an answer to this puzzle. And the answer maybe is even relevant to experiment, but I think it stands on its own feet as a piece of physics without relation to experiment. Now, in order to be related to experiment, we capitalized on something quite interesting that arose here. There was some thing that should not be discussed, some question about how does the dephasing of electrons, the rate for dephasing of electrons behave at low temperatures when temperature goes to zero. Theory says, of course, that it must the dephasing time must diverge, because at zero temperature you have no phase space for scattering. Experiments always show a saturation due to all sorts of artifacts. Some unfortunate people said that this is a fundamental thing, and some people even talked about dephasing by zero-point motion, which is a blasphemy in my opinion. And then better and better experiments show that in fact this is wrong, and it goes and goes and increases. The difference between these experiments and those experiments was in elimination of something which always happens in life, and is a minute amount of which are detrimental here, and that will be, the motivation for what I'll talk about. a very small amount of magnetic impurities in the system, magnetic moment, which can be reversed by a conduction electron, at zero magnetic field, it's the two degenerate states of spin half. This can dephase an electron, doesn't cost energy, and therefore can occur at low temperatures. So when you cleanse the system of these magnetic impurities, your dephasing rate increases. But this is very, very difficult. And even those things, if you go to lower temperatures, will saturate again. So then the thought, of course, naturally occurs, how will these things do, what will these things do to the persistent currents? Now, we turn one previous chapter. What they do to superconductivity is very, very well known. And this is a curve calculated by Abrikosov and Gorkov, 1960, I think, or 61. And of course, they said magnetic impurities break time reversal symmetry, and therefore they deteriorate Tc. So in a superconductor, the transition temperature, this is how the transition temperature goes down with magnetic impurities. Once the magnetic impurity scattering rate 1 over tau s becomes comparable to the transition temperature, Tc naught, then the renormalized Tc goes to 0. That's all the result by Abrikosov and Gorkov. Everyone knows this. Now, the question now is, what do these things do to the persistent currents? And we had very good reasons to believe that they will not do so much to the persistent current. And in fact, my message to you is summarized in this curve here, which we calculated honestly, with a real calculation, which we can stand behind. This is how Tc is deteriorating with the magnetic impurities. And this is how the persistent current is deteriorating with the same magnetic impurities. And you see there is a large range where the persistent current is almost not sensitive to the thing that kills superconductivity completely. The condition for that is that the tauless energy that I discussed before, which is the scale for mesoscopic phenomena, be much larger than Tc naught, and then the magnetic scattering rate should be in between, should be much larger than this to kill superconductivity, but much smaller than that, not to kill the persistent currents. So once you have a range, and in this copper experiment I discussed, the tauless energy was about 15 millikelvin. So nobody knows what the Tc of copper. People think it's very, very low, and I'll talk about that in a minute. But any Tc that would be on the order of millikelvin, a few millikelvin or so, and any amount of magnetic impurities on the order of a ppm, part per million or less, will satisfy this and will really put you into this thing. So you may ask, okay, what have you done here? What we have done is we actually found that two different quantities are sensitive in different ways to this pair breaking effect. One is killed completely, and the other one is not. And this is really my main message, and I hope to tell you exactly why this happens in a few minutes. So of course, first you do the calculation, you write the Hamiltonian, and just by generalizing this Amigaoker-Ekern calculation to the external magnetic impurities, you derive a very nice formula for the persistent current, which you can now, you know that it's periodic in the flux, you expand it in Fourier series, all that is very, very nice. And so, we have real results. I don't have to go into these details. And here is how the current is depressed as function of these magnetic impurities. And what we really find is the magnetic impurities depend not on the Tc that you measure for the material, but for the hypothetical Tc naught that would have existed without any magnetic impurity. That's very strange. And in fact, it suggests a method to measure this elusive Tc naught of copper, that approximation for which experimentally range over many orders of magnitude down to much less than nanokelvin. And again, I repeat, we just need this condition, that there will be a window of opportunity between the unrenormalized transition temperature and the tauless energy. And that means that you want small systems, because EC goes like 1 over L squared, as you can see on the board. As small enough L, you are really in the nanoscopic regime, and there this can happen. There is, by the way, another way to talk about it in terms of length scales, and that simply means that a pair of electrons cannot exist because they lose their time reversal symmetry on a scale smaller than the superconducting length, which is the size of the pair. But that's just a way of talking, very nice way of talking. And the experimental results really can be explained by assuming, and that's quite a bold assumption, that very pure copper, once it will exist, and it doesn't exist yet, will have a TC of 1 millikelvin. That's our kind of possible prediction. And the beauty of it is that you need less than a third of a ppm of magnetic scatterers in order to get into that regime. And I repeat that those are known to exist in real copper, and you have to work very, very hard to purify copper to even a ppm or half a ppm. So this explanation, first of all, stands on his feet. Second, is not unreasonable for real copper, but the acid test will be whether eventually people will discover this superconductivity of copper. Now I want to go back to the basic physics, which is this renormalization, which I find extremely interesting. And let me take 1 minute to remind you, or tell you, some of you, even some condensed matter physicists don't really understand this. How does this work for superconductivity? And I'll start by asking you a very naive question. You all know, I mean, everybody knows that superconductivity is due to electron-phonon interactions, which are very weak. Now, in a superconductor, there is Coulomb interaction, which is much, much stronger by orders of magnitude. How come that the little electron-phonon interaction wins against the huge interaction? Now, without this, there will be no superconductors in the world, because what this does, and I'll give you now in a nutshell the very nice insight by Anderson and Morel. What you do, you start from on the Coulomb scale, which is 10 electron volts in metals. You renormalize down to the Debye scale, which is hundreds of degrees K, 2 orders of magnitude less. You kill the Coulomb interaction by an order of magnitude or more, and then you stop and you ask yourself, who is winning now, the weakened Coulomb or the electron phonon? If the weakened Coulomb still wins, it will not be a superconductor. If the electron phonon wins, from now on the interaction is negative, and now watch what happens. The interaction is negative, this denominator is now increasing when E is small, when the running value of this energy scale is decreasing, this ln increases, this is negative, eventually it will, this denominator will vanish, and the effective interaction will diverge, and that's actually exactly the BCSTC. This ln is the reason why the BCSTC is the famous form e to the minus 1 over v. It's the point at which the renormalized attractive interaction diverges. So now you can also understand immediately why tau s larger than Tc naught kills superconductivity, because you have to stop the renormalization at 1 over tau s. After that, it doesn't work anymore, and then you never get into the divergence. And now you start also to understand what is happening in our case. If tau s is larger than Tc naught, then it kills superconductivity. But as long as it's smaller than the tauless energy, it doesn't affect very much what happens on the tauless scale. This is the basic explanation of this idea. And I think, and again, I repeat this condition, but I would like to show you a little animation which kind of brings the point home. So, these are the energy scales. Fermi energy, electron volt. Debye energy, 2 orders of magnitude smaller. Tauless energy, let's say, for a small ring, another 4 orders of magnitude smaller. Tc naught, let's say it's a millikelvin, is even smaller. Now switch on the magnetic scatterers. If 1 over tau s is much smaller than anything, not very much will happen. The Tc will be depressed a little bit. Now we increase it. Once 1 over tau s is larger than Tc naught, Tc starts to be depressed a lot. Increase it a little more. Once it's even larger, you notice how Tc is vanishing. It really disappears. So there is no Tc. Yeah, I'm finishing very quickly. But 1 over tau s is still smaller than the tauless energy. So things that happen on the tauless scale don't care so much on this magnetic scattering. So if you can take home with you this picture and try to think about it more, I think I've done my job. And now all that remains is to conclude. And you can read a PhysRev letter about it. You can read a review by Hélène Bouchia on this in Physics Journal. And the PhysRev B, the follow-up paper actually has just appeared. And all remaining now is to thank you very much.
Joe, are there questions? Yes, please.
There are some recent experimental results by Patrick Moller who seem to agree with boring quantum theory. Can you comment on that? What?
Oh, sure. This has to do with the point that I mentioned that I presumably did not emphasize enough. You know, there are two different issues. There is the persistent current in a typical one ring, which can be positive or negative at small flux. And that is described quite well by the non-interacting theory. And it's the same order of magnitude as the things I'm talking about. But if you go to 10 million rings, these things have random sign. So the total signal from 10 million rings should be smaller by 3,000, and therefore not observable at all. And that's the issue that I'm talking about. For single rings, there is no problem. Everything gives you on order of the Thouless energy, and the experiment gives on the order of the Thouless energy. The first experiment gave a little more, but now it's all cleaned up, and Catherine Moller's experiment actually, and the new Jack Harris experiment actually have really killed this problem completely. No problem at all with the single ring thing, only with the ensemble average.
So can I ask a question about the persistent currents in semiconductor rings? Assume you have a semiconductor ring where you just have 1 or 2 or less than 10 electrons. Would there also be this effect that becomes relevant?
Okay, that's a very interesting question. I think if we believe that these semiconductors will not become superconductors eventually, then all I've talked about is not, if they don't have an attractive interaction, is not relevant. However, you may remember that there are speculations by some theoreticians of certain semiconductors that can become superconductors. The best example is strontium titanate, which actually is a grandfather of ITC, which was predicted actually by Marvin Cohen to be a superconductor based on calculations and estimates, and actually was found to be a superconductor. I think it's sub 1 degree K. There are calculations, I think, by Hanke, saying that even more conventional things like silicon with the right doping can get to superconductivity. So I think this is really extremely interesting. And I think what I've talked about may be relevant in the sense that difficult as those experiments are, if I'm right, you can detect superconductivity at temperatures much above by looking at mesoscopic persistent currents. So that might be a way, to see whether whether doped silicon can have superconductivity at extremely low temperatures. So all that is really futuristic, but I think worthwhile. Thanks.
Yes, please.
Is the reason that this persistent current doesn't average out for this large ensemble, is it because the sign is the same, that it's almost there?
For the interaction, yeah, the interaction gives you a definitive sign, and the sign is actually determined by the sign of the interaction. Attractive interaction is diamagnetism because it's superconductivity. Repulsive interaction is just proportional to lambda, is a paramagnetic.
Okay, so let's thank Professor Imry again for your talk.